All right, so we started this unit with circular motion as it applies to orbits and Newton's law of universal gravitation. Now we're going to go a little more mundane and talk about just general circular motion like this. Today we're going to focus on uniform circular motion, which, like we talked about yesterday, is constant speed, constant radius. Tomorrow we'll talk about non-uniform circular motion, where the radius will be constant because it has to be to have a circle, but then the speed won't. And that'll be things like vertical circles, like this. The speed of this object is not constant, but the speed of the object here is constant, approximately. Okay. Now, what I first want to do is talk about horizontal circular motion, and that's this kind, right? And let's assume, and it's kind of interesting because you might not believe me, but there is no speed. The faster I spin this thing, right? If I only spin it kind of slowly, it's kind of traces out a cone here, right? And the faster I spin it, the more horizontal it gets. Theoretically, there's no speed. I can spin it as fast as humanly possible. I can make a machine spin it as fast as possible, and it will never be completely horizontal. It will always be have a little dip in it. I'm exaggerating here, but there's always a little dip, theoretically. And we'll see why when we talk about the flying pig here in a second. But let's neglect that for now, and let's assume maybe we're out, and because there's gravity, right? Gravity pulls down. So that's why. So let's assume that we're way out in the middle of space, far away from any source of gravity, so that the value of g, little g, at our location is 0. And let's talk about a circular motion of an object at the end of a string in that case. Okay. And let's just do an example problem. And all the problems we're going to do today, except for the last example problem, which you have to do it at home. You have to follow along and submit your solution as I go through it. You're going to do it as well and then submit that for attendance. But the first one, let's just talk about an object on a string. And, the problems we're going to deal with are going to be purely symbolic. We're not going to use any numbers. Okay, it's going to just be based on the variables. So I have this object on the end of a string, and it will be moving in a circle at constant speed. So we'll have uniform circular motion, UCM. We'll have a radius. I'm going to use big R now. Get used to seeing big R and little r both being used interchangeably for radii. We'll have radius R. We got a mass m. And let's say it is uniform circular motion with period capital T. And let's say that we need to determine the tension in the string. Okay. And express your answer. Get used to seeing this because we're going to see this more and more as we go on. And then as you travel further in your careers as future physicers and engineers, you'll be seeing a lot of problems like this. Express your answer in terms of other variables. Express your answer in terms of the given quantities, m, r, period, and any fundamental constants. Fundamental constants for us, usually at this point, it's pretty much just little g and big G, right? Last year, it could be the ideal gas constant, Avogadro's number, things like that. All right. Now, it does have this list of things that your answer can be expressed in. That means that you can't have any other variables in your answer. Okay? It doesn't mean that you need to have all of these variables. Sometimes this answer I might be able to write in just terms of R, T, and G, and maybe not mass M. So don't freak out if you're like, well, my answer doesn't have one of those. That's fine. Your answer just can't have anything other than those. All right? Okay, well, here, I'm going to draw, this isn't technically a free body diagram because free body diagrams only have forces on them. But I'm going to go ahead and just draw my tension force right here. And since I brought that up, before I go on, let me point something out. I am grading the free response questions from the last test right now. Nothing but forces goes on free body diagrams. If you put a velocity vector on a free body diagram, you will lose a point. If you put an acceleration vector on a free body diagram, you will lose a point. In the scoring guidelines for those questions from the College Board, They always say 1 point is awarded for each correct force vector. 1 point is deducted for each incorrect force vector down to a minimum of 0. So if you have a question that has if you have to draw a free body diagram that has one force and you draw that one force and then you draw a velocity vector attached to the dot, then you got 0 points for that. Because you get a point for the correct one, but then you get a point deducted for the incorrect one. Only forces. Free body force diagrams. Only forces. Okay. Also, since we're on the subject, show your work. You guys got to show your work on the FRQs. Some people just wrote the numerical answers to the questions. That is not okay. First of all, if you got the answers wrong, obviously you don't get any points for that. You don't get any points for the work. If you got the answers right, I'm not giving you points either, because you probably just copied that from someone and didn't bother showing any work. So, and if you didn't do the free response questions, then you get a whole lot of 0 points for that. So yeah. In the future, take a little more time on those free response questions. They are worth way more than any individual multiple choice question on those exams. All right. So this isn't technically a free body diagram because I've drawn a string attached to it and stuff like that, but I'm just using it just to save a little time. All right, so I need to calculate the tension force. And so I'm going to start with Newton's second law of motion. Why Newton's second law? Because I have an object that is accelerating in response to a non-zero net force. So I start with Newton's second law, which says the net force is mass times acceleration. This is why this unit's kind of short, because we're just building on something that we literally just learned about and spent a whole lot of time on. The only thing that's different is I have this object. It's moving in a uniform circular motion. That means it must have a centripetal acceleration. So I can put a little c there on the acceleration. And that must be in response to a net centripetal force. So I can put a little c subscript on the force. Want to be super technical, I can put vector arrows over the force and the acceleration. Those are both forces or vectors that must be pointing in the same direction. Now, never label on a free body diagram a centripetal force as F sub c. Any force can be a centripetal force. Tension, in this case, the gravitational force in the case we've been talking about. So in the next step, this is just writing. And again, show equations first too. Don't just start by writing numbers on your FRQs. Write the equation. The scoring guidelines generally say something like the student recognizes Newton's second law applies. And how can you indicate that to the grader? By actually writing Newton's second law before you do anything else. In the next step, though, I need to say, well, the net centripetal force is because the centripetal motion is happening because of the tension force. So I just replace that with the tension force. It's only one, just one force. That's going to equal the mass times the centripetal acceleration. All right, well, I can have m in my answer. Remember, I'm looking for the tension force. I can have m in my answer, but I can't have the centripetal acceleration in my answer. Thankfully, we all remember that we have an expression for the centripetal acceleration. It is the speed squared divided by the radius of the circle that the object's moving through. Again, if you want to know where that is, take AP Physics C next year. We actually prove that, and it's a fun proof. It just requires a little bit of calculus. So you got to take my word for it now. It is on the formula sheet. So I'm going to make that substitution. So when I substitute v squared over r for the centripetal acceleration, I get that the tension force is mv squared over the radius. That's still not good though, because while I can't have the radius, I can't have mass, I cannot have the speed v. And this is not on the formula sheet, but hopefully you've either committed it to memory or you can just work it out. If I have an object that goes around a circle exactly once, then it's traveled the circumference of that circle. And we call the time required to travel around the circumference exactly one time the period of revolution, which is the symbol t, capital T. So I can say that the speed, and this is just distance over time. We learned that in middle school. Distance over time, it just so happens that we're dealing with the distance of one circumference and the time period, capital T, that it takes to cover exactly one circumference, one revolution. So I can make that substitution. And for those of you that aren't the best at algebra, I understand that some people just don't really like algebra too much. But if you're like me and you haven't done this before, you've done this a million times, I'm going to do this. I'm going to take it slowly. And I'm going to just substitute this in for v before I do anything else, so I'm not thinking too hard about anything. I just substitute that in for v, although it must be squared, divided by r. A lot of you are in pre-cal or have taken pre-cal with Miss Burke or Miss Garcia. They would not be happy with an answer written like this because this is a compound fraction, so you must simplify. So the first thing you do, PEMDAS, exponent. Do the exponent. Right, nothing to do in parentheses, so I'm going to apply that exponent. And you should know your properties of exponents. Now when you have multiple factors raised to a power, then each factor gets raised to that power. If you can skip some of these steps, by the way, because you are pretty good at algebra, that's fine. That's fine. I know most of you are probably, or a lot of you at least, are pretty good at algebra. So I have mass times, when I square everything in here, I get 4. Pi gets squared. Radius, I should use capital R. Let me be consistent here. Radius squared divided by period squared, all over the radius r. And I'm going to simplify the numerator here first. Again, if you can skip some of these steps, that's fine. If you like putting the m over 1, just to remind you that you got to multiply the numerator straight across and the denominator straight across, that's fine as well. And so whenever I do that, I get that the tension force is equal to 4 pi squared times m times r squared. Right? Commutative property of multiplication, you can do any order, write them in any order, over the period squared divided by radius r. Some of you might not be able to see that. Let me write this up here. Sorry. So I get tension is 4 pi squared m r squared over the period squared divided by radius r. Your pre-cal teachers definitely wouldn't be happy with it written like that either. So this is still a compound fraction. I can make it obviously a compound fraction divided by another fraction by just putting r over the ninja 1, the making it a compound fraction. And then we can, as Mr. P likes to say, flip the guy and multiply, or just multiply the numerator by the reciprocal of the denominator. So that's 4 pi squared m times r squared over the period squared times 1 over r. And I got a numerator r, 2 of them actually, and a denominator r. So one of the numerator r's cancels with one of the denominator r's. And then I have an expression for the tension force equal to 4 pi squared times the mass times the radius of the circle divided by the period squared. M, R, T, and pi and 4, just numbers. That's fine. So there's my answer. And you box it. On FRQs, box your answers. Make that a habit and carry it with you into college. You want to make the people that grade your work, you want to make it as easy on them as possible. Not just to make their lives easier, but to make sure that when they're on the fence, and whether they give you the credit or not, if you're making it easier on them, they're more likely to err in your favor. Some students memorize this because it does pop up somewhat frequently. I never have memorized it. I did today just because I've done it a couple times today, but I'll lose it again. But you want to be able to generate it. It's just Newton's second law. Literally just Newton's second law with this one new thing. This is not new. This is not new. This is distance over time. You just got to know that you got to know your geometry of a circle, but really you don't even need to know the geometry of the circle because on the formula sheet you have circle circumference right there. Okay. All right. Any questions about that one? Can I erase up here then? Well, let's talk about Wilbur. You guys ever heard of Mr. Ed? No. It was before my time, so definitely before your time. All right. You know Wilbur from Charlotte's Web, though, right? Here's Wilbur. He grew some wings. He's flying in a circle as well. Now you guys know what a pendulum is, right? Pendulum, this is a pendulum. Swings back and forth. So this, what Wilbur's doing, or something that looks like this, is what's called a conical pendulum. Because it's essentially doing the same thing. It's going back and forth, but it's tracing out a cone, the shape of a cone, right? All right, he'll keep doing that for a while. The thing is that the wings do not provide the centripetal force. They do not provide any type of lift. They do not aid in the moving the pig up. They're only there to counteract the air resistance that the pig encounters as it flies around. Okay? So that's why the wings are there. If the wings aren't flapping, and to keep him pointed straight. The wings aren't flapping, he travels in the cone, but eventually it dies down and he hits that. And, oh yeah. So the wings are there just to keep him moving in a circle of constant radius at constant speed. It essentially negates the air resistance and just keeps him oriented. Okay? All right. So again, that's what's called a conical pendulum. Conical pendulum. And as we analyze this conical pendulum, we will realize exactly why it's literally impossible, theoretically impossible, to spin an object around so fast that the string becomes perfectly horizontal. Okay. What's that? Oh, and yeah. If you're away from gravity, then yes, you can do it. But on the surface of the Earth here, you can't do it.
I mean, there'd still be an amount of force acting on it anywhere, right?
In the universe?
Yeah.
There are places where g is close enough to little g is close enough to zero that you can completely neglect it. There's a point right between the Earth, somewhere between the Earth and the Sun, that the force of gravity on you would be exactly zero. Yeah. And you wouldn't feel any force, but you would be that's unstable equilibrium. If you just got perturbed just a little bit in one of the other directions, then you would.
In the middle, like where the gravitational force goes zero, because like it doesn't have a negative.
Yeah. Okay. So conical pendulum. I'm gonna go ahead and draw my situation again. This won't be a true free body diagram. I'm gonna use it for just illustrative purposes. So there's my pig. And let's go like this. And so before I go on, just tell me what the free body diagram should look like. What forces are acting on the pig? And let's neglect our resistance and the wing thrust force. Force of tension, which points up in the direction of the rope. That'll be my tension force. And then the force of gravity, mg, pointing down. Right? All right. And let's say the question says this. Let's say the question says calculate Wilbur's period of revolution in terms, so express your answer in terms of the following. Now I'm gonna do something real quick. I'm gonna say, all right, this is the radius of the circle, obviously. I'm gonna say that Wilbur is this height, call that h. This height, right? The height of the pivot point, essentially, the connection point above where Wilbur actually is. And then I'll call the length of the pendulum, I'll just call that length L. Okay. And let's say the problem says calculate Wilbur's period in terms of H, L, and any fundamental constants. And you might scratch your head a little bit when you read a problem like that, because you're like, all right, well, I know Wilbur's got a mass m. It's probably might even be given to us or put on the diagram. I know I got a radius here. Radius isn't there. I know that there's an angle that I'll probably be using. And usually in conical pendulum problems, they give you the angle with the vertical that it makes, the string makes. So that's not in there, right? So the thing is, when you see problems like that, when you see problems that say express your answer in terms of all this stuff, or these just couple things that that you see there's more of in the actual problem, but it says express your answer in a smaller number of variables, chances are you're going to cancel some stuff out, right? Things will cancel out. And so don't freak out when you see a problem like that. Just work through the problem, and then hopefully by the end, you'll be able to hash out why those things shouldn't be in your answer, okay? And then as in what we'll see in this problem, we can use our geometry skill to actually rewrite some stuff in a way that gets rid of things that can't be in our answer. Okay. All right. So, first thing I think, I have this force pointing down, this force up at an angle. What am I going to have to do here? I'm going to have to decompose. And when the force is acting down here, this is just me. You don't have to do it this way, but I feel like it's conceptually the easiest way. If I have the force acting down here and I got the angle up here, that confuses me. So what I like to do is, all right, well, I'm just going to figure out what this angle is. This angle is same as that angle. I have this vertical line. They're sliced by the transversal, which is the length of the pendulum, creating alternate interior angles that are congruent. So I can definitely decompose in terms of that angle there. So I'll write the upward tension force and the horizontal tension force. Notice that the upward tension force, the vertical component of the tension force, is the cosine component, right? It's the adjacent side. The horizontal one is the sine component. It's the opposite side. A lot of students tend to get stuck in whenever they do horizontal motion. They tend to stick to cosine as horizontal and sine as vertical. No, it has to do with the orientation of the triangle in relation to the angle. The angle's here, the opposite. Sine is opposite. So it's going to be the hypotenuse, the tension force, times the sine. The adjacent one is the cosine component, regardless of how the triangle is oriented. Okay? So I've decomposed my vectors. Well, I drew my free body diagram. I decomposed my vectors. Now I'm going to apply Newton's laws of motion. Right? And the question is asking for the period. So, and I'm using my standard coordinate axes. I like starting in the direction that the question is actually asking about. And so if it's asking about the period, am I worried about the vertical motion or the horizontal motion? The horizontal motion. So I'm going to go ahead and start by saying the net force in the x direction equals the mass times the acceleration in the x direction. And I'm going a long way here. I'm just showing every step here. The net force in the x direction, I only have one force in the x direction. It's the tension times the sine of the angle, right? Tension force. And let me write it this way. I notice, when I look at Newton's second law for the x direction, I notice it's centripetal motion. And so I can even do this, right? In the next step, just substitute those in for it. You don't have to do that. This is just going very methodically. The net centripetal force, again, is just due to a single force, the tension times the sine of the angle. And I'm looking for the period, but I don't see the period in this equation, even though I know it's dealing with the horizontal motion. So I just got to do the same substitutions that I already did in the last one, right? So I'm going to, since we already did that, I'm just going to do it now. It's going to be 4 pi squared mr over the period squared. That's what the result from the previous one is, right? Okay. So I could solve this equation for t, but I'm going to have a lot of problems. I have an m, I have an r, I have a theta, and I have a tension force, right? One of those I can take care of, kind of. I can rewrite something up there in order to get rid of one of the variables. If that's not obvious, we'll come back to it. Okay, we'll come back to it. All right, so look at the vertical forces, the net force in the y direction. That's going to be the mass times the acceleration in the y direction. What's Wilbur's acceleration in the y direction? 0. He's not accelerating. He's at rest in the y direction. So this side becomes 0. I have a positive tension times cosine theta. I have a negative weight force. Those added together must be 0. Add mg to both sides, and I get that the tension force times the cosine of the angle equals the weight force mg. So I got 2 equations. As Mr. P likes to say, you can put those equations in your equation holsters, because he's funny.
Divide by little g and you'll get m, and you can substitute out for m.
You can do that. That's it. So go ahead and do that if you want. But I don't want to. If I solve for m, then I get a fraction. Then I'm putting a fraction here. And if you're fine with compound fractions, that's fine. Go ahead and do that. There's multiple ways of going about doing this. What I see first of all, what I see is that I can get rid of theta in both of these equations by making a substitution. We haven't done this in this class, but we've done this in geometry. What can I substitute instead of sine theta? Look at the triangle.
R and the H correspond with the FT sine and the FT cosine. So it would be the R, right?
Well, I can't just put in R for theta. Sine of theta is equal to R over
that, yes.
over L. The sine of the angle, is that what you said?
Yeah.
Sine of the angle is R over L. So I can plug that in. Tension force times R over L. R over L. We haven't done that when we've done vector decomposition in this class, but that's literally the definition of theta. It's the ratio of the opposite to the hypotenuse of our right triangle. And so that's going to equal 4 pi squared m r over t squared. And so I can replace cosine theta with what? H over L equals mg. Ah, now I got, H and L's, now I got those in here. So I'm probably getting somewhere. Now what I would do here, well actually everyone brought something to the party in this equation. Everyone brought radius to the party. Notice how radius is not in either equation anymore. Ah, good. Because radius isn't in our list of things that can be in our answer, so it's good. It's good that we got rid of that. All right. So at this point, what I would do is solve the tension force here, solve this for just tension, right? And then plug what I get in for the tension here. So to solve for the tension here, did I do this right? Cosine.
Just multiply both sides by.
Multiply both sides by L over H, right?
Yeah.
So numerator L, denominator L, numerator H, denominator H. So I get an expression for the tension. It's going to be mgL over H. And then I'm going to plug that guy. Plug that in for the tension force here. And then rewrite it. So I just substitute that in. So I'll have the tension force, which I know is mgL over H. And then that gets divided by the length, right? And if I divide that by the length, well, I'll do it the long way. And so that's going to equal what I have on the right side, which is 4 pi squared m over the period squared. Well, remember I can make, this is a compound fraction. I can put it over the Ninja 1. So I flip the guy and multiply. So I get mg times L over H times 1 over L equals 4 pi squared m over the period squared. Now what happens?
The L's cancel.
The L's cancel. And the m's cancel. Ah, now we're getting somewhere, right? What was that? Everyone brought mass to the party and L. Well, no, not L. Sorry. That just cancels because it cancels. So I get G over H equals 4 pi squared over t squared. Now we can solve for t. Did I do that right? I feel like I made a mistake. What's that?
Yes, pi is a constant. It's a 2.14.
Pi always equals to conical.
It's usually it's just a number. It's a transcendental number.
Yeah.
It's an irrational number. It never changes though. All right, so we can solve this now for the period. I can multiply both sides by the period, right? Are we okay with me cross multiplying here?
Yes.
Can I? You want to get to this point before too long. You want to be able to say this. T squared is equal to 4 pi squared h over g. Right? I just multiply both sides. Are you okay with that? Do you want me to work through that? I can work through that if you want. Multiply both sides by h over g. So it puts h over g on this side, cancels on this side. Multiply both sides by t squared, cancels over here and puts it in the numerator over here. And then I just square root it, square root both sides. So I get that. And if you're in pre-cal, Ms. Burke wouldn't like that answer. How could you simplify that?
2 pi
Square root of h over g. I think I messed up last period because I don't think that's the result that we got. That's why I was second guessing myself. Sorry, second period. Maybe not, I don't know. Interesting result here. What does the period of Wilbur depend on?
2 pi.
Well, 2 pi, yeah, that's just.
The height.
Well, what variables?
Height,
Just the height h
not the length.
and the value of g, not the length, yeah. What that means, there's significance there. Remember, anytime things cancel out, there's significance. The mass of the guy doesn't matter. Now, if you're spinning it around, if it's more massive, you're going to have to spin it harder to get it up to the same position. But from the perspective of this guy's motion, the radius doesn't matter. The length of the pendulum doesn't matter. It just has to have this height. So that means if you have a longer pendulum, you just got to spin it faster so that it rises up to that same height. And then it will have the same period. It'll be moving faster. It'll be covering more ground, but it will have to be moving faster in order to do so. If you shorten the pendulum, then you just start spinning it less fast. So it falls down and makes a steeper cone. So it moves down to here and it moves more slowly because it's going to cover smaller distance, but it will have the same period. Okay. Always be on the lookout for that. When things cancel out, like the length, the mass, there's physical significance there, and you want to make that connection to the real world. Cool beans? It's weird seeing you here, Kurt. All right. Any questions about that? It's fun stuff, right? Fun stuff. Just let this absorb tonight, by the way. There's no new assignment. So this is just internalize this. Feel it. Feel it. Can I erase everything?
Mm-hmm.
All right. Now we're going to do a common engineering problem. And it will be on the last page of the notes that I gave you the other day. If you don't have them, it's all right. You don't need to have them with you. Okay, so it's going to be example 4. It's going to be a car rounding a curve. The bullet point above example 4 just talks about centrifugal forces, which again don't exist like we talked about yesterday. So yeah. What I do want to point out though, on a flat road, the force that causes the car to turn whenever you turn the steering wheel, it's not you turning the car by turning the steering wheel. You're not strong enough to. You can't provide that force. Well, maybe Alex can. You're not strong enough. What you do is just turn the tires. You redirect the tires, and then the friction force between the tires and the road grows to a large enough force to actually redirect the tires. But understand that it is static friction. It's static friction. A lot of students, because they know the car's moving, kinetic friction. Now, you don't want kinetic friction between your tires and the ground. If you look at the tire as it's rolling, when it's rolling, the surface of the tire is in contact with the ground and it is not sliding. Okay? If they're not sliding, then it's static friction. They're in static contact, but the tire rolls over the ground. And so that's why you get the motion. If you have kinetic friction between your tires and the ground, what's going on?
You wouldn't have tires for very
You're skidding out or you're burning out. Yeah. And that's why if you're racing, you don't want to burn out your tires. Because when you burn out your tires, you're not going to get the same acceleration that you would if you didn't burn out your tires. You got to find that balance, right? Not that any of you guys race. I imagine. Like real race?
We use physics in race systems.
Anyway, so it is static friction that causes you to turn. And remember, we talked about friction is what gets your car to actually move, right? Your engine is just used to spin the tires. It's the interaction between the tires and the ground which provides the friction force that makes your car go forward. Okay. If there's not enough friction, right, you have rubber tires and asphalt surface, there is a maximum friction force that can act on those tires. And if you like for a certain speed, there's going to be a maximum static friction force that can be exerted. And if that friction force is not enough to keep you from sliding, you will start to slide. Okay. Like it says, if there's not enough friction, the car skids out of a circular path and into a straight path. And then you're in trouble. So example 4 says, and this is a very common engineering problem. Whenever you see speed limits posted on like off-ramps and on-ramps or curved parts of highways, they calculate the maximum speed that you can take those curves with and then determine what that speed is and then definitely lower it for the speed limit because they know guys like you guys are going to be speeding out there, right? Yeah, they post maximum
We
speed.
know you're gonna speed, so
Yeah, it's usually significantly higher than what you see posted. Anyway, let's work out this problem to show why. So example 4 says you have a car of 1,000 kilograms, rounds a curve on a flat road of radius 50 meters. Notice in the diagram, the road is not a circular road. The road just has a circular arc within it. Okay, so keep that in mind. It doesn't need to be a circular road. It just needs to have an arc, circular arc. At a speed of 50 kilometers per hour, for the sake of time, I'm going to go ahead and convert that because we don't want kilometers per hour. We want meters per second. So in 1 hour, there's 3,600 seconds. In 1 kilometer, there's 1,000 meters. Kilometer, numerator hour, denominator hour, meters per second. Okay. And in your head, what does that call? 13.9. 13.9. So this is the speed that the car is going to round the curve in. And then the question says, will the car make the turn or will it skid if A, the asphalt is dry and the coefficient of static friction is 0.6, and then B, if the pavement is icy and the coefficient of static friction is 0.25. Now let me just give you a visual for this problem before we actually go through the solution. So here's our circular arc. Again, this isn't a free body diagram. This is just the diagram of the car. And then I'm going to label it with the velocity and the force. But because it's not a true free body diagram, I'm allowed to do that. You can't do that if it's a question on an exam that says draw a free body diagram. So it's moving this way, and the centripetal force is going to be towards the center of the circle, and that is going to be the static friction force. We're not dealing with kinetic friction here. Well, we kind of are, but I'm just going to put it as the friction force. Let me be. It's the Fs, comma, S. Static friction force. Now, you should be able to understand that there is a maximum speed that you can take a turn in your car. You got to be able to understand that. And then you got to make a connection. You know, this class, hopefully you realize at this point, it's not memorize the equation or look at the equation, plug in numbers, and come up with your answer like lower level math classes are. Your math classes aren't like that either, you probably have noticed. This is a class where you got to engage your brain and connect it with what we're learning up here, with the mathematics, with the concepts. So what you need to understand is that you can have a very small static friction force. If you're not moving very fast around the curve, the static friction force is going to be very small. Just like when I push on this device here. I push on it with very small force, I get a small static friction force. If I push hard enough, then it starts to slide and becomes kinetic friction because I've exceeded the maximum static friction force. So this static friction force can be small, it can be bigger, and then it can get to some maximum amount. And what you need to understand, the mental connection you need to make, is that the maximum, this one's done, the maximum static friction force, Fs max, corresponds to the maximum speed, right? When I'm at the maximum speed that I can take the curve with, the car will be experiencing the maximum static friction force. If I go any faster, then I've exceeded the static friction force that can be exerted on my car, and it then becomes kinetic friction and it starts to slide. So this is the mental connection that you must make in order to solve this problem. And remember that when we learned about static friction force, the static friction force is the inequality one. It's less than or equal to the coefficient of static friction times the normal force. So it can be 0, it can be above 0, it can take any value up till it gets this value, and it can't be any higher. Okay? But then that lets us know that the maximum static friction force is exactly equal to the product of the coefficient of static friction and the normal force. So with that information, all I need to do is apply Newton's second law. The net force is going to be the mass times the acceleration, but we are dealing with centripetal forces and centripetal accelerations. There is a normal force and a weight force on the car, but they don't contribute to the centripetal force. They're pointing in perpendicular directions. So the only centripetal force here is the static friction force, and we are looking for the maximum static friction force because we know we're trying to find the maximum speed. Okay? This is how fast we're going, but we want to find out what the maximum speed is to see if at that speed we're going to skid out or not. So the maximum static friction force is equal to mass times the maximum speed squared divided by the radius of curvature. So when I put Fs, the friction force maximum, I put the velocity maximum. Okay? And make sure I put those two together. Static friction force, the maximum is the coefficient of static friction times the normal force. That's going to equal the mass times the maximum velocity squared over the radius. Now I don't know the normal force, but hopefully you can see it's pretty easy to find the normal force. If I look at the car from the top, these are the forces. But if I look at the car from behind, maybe, there's the car from behind. Obviously you have the friction force that points this way on the car, but you also have the weight force and the normal force. And just by looking at this, I know that the normal force is the same as the weight force, right? So I can plug mg in for the normal force. So I get the coefficient of static friction times mg equals mass times the maximum speed squared divided by the radius. Everybody brought mass to the party. That's it. There's an interesting result, or an interesting phenomenon right there. Notice how there's not different speed limits for different types of cars. As long as you got the normal tires that aren't like super high-tech engineered. A little smart car, which I don't recommend you ever buying because I can only imagine getting a wreck in one of those. A little smart car and a big F350 turbo diesel, right? Those two cars are going to skid out at the same speeds because their masses don't matter when it comes to the maximum speed. Okay. Then I just multiply both sides by r. And then numerator r, denominator r. And then I get that the maximum speed squared is equal to the radius times the coefficient of static friction times g. Square root both sides, and you get that. Notice I haven't plugged in any numbers, right? Because I have to check in two different cases. This is pretty indicative of why it's very useful to solve symbolically and then plug in the numbers at the end. Because now all I need to do is use the two different coefficients of friction in the same equation, right? So when it's dry, the maximum velocity is the square root of the radius, which is 50, times the coefficient of friction on the dry asphalt, which is 0.6, times 9.8. And when it's icy, I use the same equation. It's going to be the square root of 50 times the coefficient of friction on the icy road, is 0.25, times 9.8. And someone in here can do this in their head, right? Times 0.6 times 9.8 square root. On dry, I can take that curve at a maximum of 17.1 meters per second. Any faster and I skid. On icy, 130? Oh, okay. It's about 11.1 meters per second. So on the dry ground, I can take that particular curve at 17.1 meters per second without skidding. So do I skid? No. I'm below that speed. If that same surface is icy, my maximum speed is 11.1 meters per second. Am I skidding on that surface? Yes. Take home point, know the physics. Other take home point, change your driving habits when the weather changes. If you haven't changed your tire pressure, by the way, it's gotten a lot colder. You need to put more air in your tire, right? Same number of moles of gas. The temperature has gone down. The pressure has gone down. So you need to put more ice in, more air in. And also when it rains, guys, when it rains, the coefficient of friction gets reduced because the water fills in the little hills and valleys that create the friction forces. So when it's raining, slow down. When it's icy, slow way down. People that do not change their driving habits when the weather changes drive me crazy because they are endangering my life in addition to their
I
own.
just think hydroplaning is fun.
It is, if you're doing it safely away from anyone else and not endangering anyone else or their property. Have a good day, guys.